Good morning, everyone. My name is Arjun Viral. Today, I'm going to talk about something that is really important in the world of cloud computing and cybersecurity, which is the VM isolation techniques and how they prevent cross VM attacks. Now, before I start, let me ask you something. When you see any cloud service, whether it is Gmail or Netflix or Amazon or any banking, do you ever think about what's happening behind in the backend servers? In the backend, what's happening? The data is sitting on a server somewhere in the world. And here's the interesting part on the same physical server. There might be hundreds of other virtual machines belonging to completely different companies and different peoples. So the big question is, how is your data kept safe from all of these virtual machines sharing the same hardware? That's exactly what we are going to explore today. We will understand how virtualization works, what kind of attacks can happen when the isolation fails, and what techniques engineers use to keep virtual machines completely separated from each other. Uh, this is a topic that combines our computer architecture, operating systems, networking, and cybersecurity all in one place. So let's get into it. So let's we move. Let's see. I will tell the overview of this presentation. So this is the overview. So if we look into that, what we are going to see today is visualization basics. First is the visualization basics, in which VM architecture, what the hypervisors will do, and the isolation fundamentals, uh, and why isolation matters. Which are the things we are going to see in the visualization basics. And the second is the cross VM attacks, in which we can see the attack types, threat model, and real world incidents, and the isolation mechanisms, memory isolation, CPU isolation, and network isolation, and storage isolation. These are the things we are going to see in the isolation mechanism. And the slide channel attacks. Slide channel attacks are the cage timing, row hammer, and the spectre and the meltdown, which are special and a very sneaky category of attacks that are extremely hard to defend against. Then advanced defenses, including cutting-edge technologies like trusted execution environment and micro VMs. And finally, a comparative analysis of all these techniques, which one worked best and what trade-off you have to make. So let's begin. So first is the VM virtualization and the VM architecture. Visualization creates an isolated abstract computing environment on shared physical hardware. So what is visualization? Imagine you have one very powerful physical computer. Uh, instead of instead of just one operating system on it, visualization allows you to run multiple operating systems simultaneously on the same physical computer. Each one completely isolated from others. Each of these are called virtual machines or VM. Think of it like an apartment building. One building, that's your physical hardware. Many apartments inside, those are your virtual machines. Each apartment has its own walls, its own door, and its own key. The resident of the apartments 3A cannot walk into the resident of the apartment you know 2B or 5B. So like that. The separation is isolation. Now the software that makes all of this possible is called the hypervisor, also known as a virtual machine monitor or VM. So the hypervisor sits between the physical hardware and the virtual machine. It acts like a building manager. So it decides which VM gets how much utilization of the CPU, how much memory, and how much storage it should get, and keep them separated always. It makes sure no VM can interfere with another. There are two type of hypervisors. So first type is the bare metal hypervisor. This runs directly on the physical hardware. with no operating system underneath it. Examples are the VMware, ESXi, Microsoft Hyper-V, and Zen. These are the examples. This is what big cloud providers like AWS and Azure will use. It is fast and very secure. Okay. Now the next type is the hosted hosted hypervisor. This runs on the top of the normal operating system. So the examples are the VirtualBox and the VMware workstation. You might have used one of these on your own laptop. It is very convenient, but has a larger attack surface because there's an extra OS layer underneath it. Each virtual machine gets its own virtual CPU called a vCPU and its own virtual memory called a VRAM and its own virtual disk and its own virtual interface. So these are the posted hypervisor. Here is the most important point of the entire slide is the stronger isolation is the core security promise of virtualization. The entire model depends on the assumption that one VM cannot see or touch another VM what is it's doing. When that assumption breaks, we have a security problem here. So that we will see in the next slide. What are those? We name them as a VM cross attacks. So we'll see in the next slide. What is VM cross attacks? So what are the VM cross attacks? So in this slide, we will discuss about the VM cross attacks. Uh, a cross VM attack is a malicious, virtual machine. Virtual machine manages to exploit shared resources or vulnerabilities to the in the hypervisor to access, disrupt, or steal data from the another VM in the same physical host. Let's go back to our apartment building analogy. A cross VM attack is like a resident in one apartment finding a secret passage through the wall into the neighbor apartment and reading their private documents. The walls were supposed to be solid, but they were, you know, there are six types of this is called the VM cross attacks. For example, actually. So there are six type of VM cross attacks. Each one exploits a different weakness. First is the hypervisor escape. The hypervisor escape is this is the most dangerous. Here a VM actually breaks out of its virtual boundary and gets direct access to the hypervisor or other VMs. If you escape the hypervisor, you essentially have the control over the entire physical machine. So they can get access over entire physical computer. And the second is the side channel attack. These are very clever and very sneaky. Instead of directly breaking in, the attacker observes pattern. Things like CPU, cache timing, memory access, patterns, and power consumption, and uses this observation to figure out secret information like encryption keys. The attack doesn't touch your data directly. It just watches how your VM behaves. And the third one is the memory-based attack. This exploits shared memory regions. Some of them, some of the hypervisors are uses a feature called memory deduplication, not duplication, deduplication. If two VMs have identical memory pages, they share one physical copy to save space. Attackers can exploit this to figure out what's in another VM's memory. The fourth one is the network access. Co-resident VMs on the same host share a virtual network switch. Attackers can exploit vulnerabilities in the virtual switch to intercept or inject network traffic from neighboring VMs. Fifth is the storage covert channels. By watching disk access timing patterns, uh, a malicious VM can actually encode secret messages and communicate with another VM or infer what another VM is doing through the timing of I/O operations. These are the storage power channels. And next is the memory-based attack. The the memory-based attacks is the simpler but still harmful. A malicious VM floods the CPU, memory, or I/O resources so aggressively. that neighboring VMs are starved of those resources. This is basically a DOS, denial of service, against your cotenant. These are the memory-based attacks. Now, next is the now what we are going to see is the attack taxonomy and the real-world examples in the next slide. So let me show you the real-world examples of these attacks because these are not theoretical; these are actually happening. So let me put them. So here is the attack CVE, type, target, and their impact security. We'll see one by one. First is the Spectre Meltdown 2018. These are probably the most famous security vulnerability in modern computing history. They exploited the way the modern CPU is, the way the modern CPU is speculatively execute instructions. A malicious VM could read kernel memory from another VM through case timing channels. The severity was very critical. Every major cloud provider every major cloud providers like AWS, Azure, GCP has to do emergency patching. Billions of devices were affected in that time. Now the next is the Rowhammer attack. The Rowhammer attack, this attack targets the physical DRAM memory chips by rapidly reading the same memory location millions of times per second. You can cause electrical interference that flips bit in neighboring memory rows that completely belong to the different VMs. By carefully causing the right bit flips, an attacker can escalate their privilege to escape the sandbox. Next is the Venom CVE 2015, uh, which is which is a hypervisor escape. This one is particularly interesting. Researchers discovered a bug in the code allowed the VM to completely escape the hypervisor and take control of the entire physical host. The scary part is that the bug had been sitting in QME codebase undetected for over 7 years. So for almost 7 years, the bug has been there, before 7 years. Next is the MDS attacks, which is famously called the zombie load. In 2019, it has been happened. This exploited an Intel CPU microarchitectural data sampling. The data was the data was leaking across the hyperthreads, meaning one process could read data being processed by the another process on the same physical code. Some cloud providers had to completely disable hyperthreading to mitigate this. The lesson from all of this is to all attacks exploit the assumption that shared hardware is perfectly isolated. When hardware and software make promises about isolation, they can't fully keep. Attackers always find the gap. So these are the attack taxonomy under the real world examples we have discussed. So now the next topic is the hypervisor based isolation. Now let's shift our focus to the defensive side. How does the hypervisor actually enforce the isolation? So let's start. Let me put the slide. This is the hypervisor based isolation. Uh, we start from the CPU. Modern CPUs have concept called the protection rings, as you see like this type of rings. Think of this as a security levels, different levels of security. Ring three is the outermost ring, least privileged. This is where your normal applications like Word document, PP, PowerPoint, PDF, Chrome, Google, this type of normal applications, low level applications will run on this. Ring zero is the innermost ring. This is very most privileged. This is where the operating system, like kernel runs, can do anything, access any memory, control any hardware, can do all of the things. Now in virtualization, we add ring one, even more privileged than the previous ring zero. This is where the our hypervisor lives. The hypervisor is the most trusted piece of software in the system. It sits about everything. The virtual machine run in ring 1 and ring 3, they believe they are in control. But whenever they try to do something privileged, like accessing the hardware, The CPU actually catches the instruction and hands the control to the hypervisor. This is called the VM exit. The next is the hypervisor looks at what the VM was trying to do, perform it safely on its behalf, and hands the control back to the VM. So this is called the VM entry. The VM never knew it was interrupted. This happens thousands of times per second, completely transparent to the VM. The machine is implemented in hardware. Intel calls it VTX, and AMD calls it as AMD V. So these are implemented in the hardware. Now then there's IOMMU, Input Output Memory Management Unit. This is a hardware component that controls you know which physical memory addresses each devices and each VM is allowed to access. It prevents malicious VM from using a passed through hardware devices to read memory that belongs to the another VM. Intel's version is called VTD, AMD's is called AMD VA. Together, the ring architecture and the IOMMU form the foundational layer of the VM isolation. So these are the hypervisor-based isolation. Now the next is the memory isolation technique. Memory isolation is the one of the most critical aspects of VM security. So let's go through the main techniques. Let me share the slide. These are the memory isolation techniques. The first is the extended page tables, which is also known as EPT or NPT. Every VM thinks it has its own memory, but physically all the VMs are sharing the same RAM. The question is, how does the CPU know which physical memory belongs to which VM? The answer is the extended page tables. These are the two levels of translation. First, the guest VM translates its own virtual addresses to what it thinks of the physical addresses. Then the hypervisor maintains the second layer of translation, mapping the guest physical addresses to the actual physical addresses. The two-level translation is enforced entirely in hardware. The CPU checks this table at full hardware speed. The VM literally cannot access memory address that is in its own page table. That is the primary mechanism preventing one VM from reading another VM's memory. So these are the explanation for the extended page table. Next is the memory ballooning. Hypervisors sometimes hypervisors sometimes need to reclaim memory from one VM to give another VM. A memory ballooning does this by installing a special driver inside the VM, which tells the VM to voluntarily release some memory. Each VM has the hard memory boundary. VM never see each other memory through this process. However, these features are called KSM, kernel same page merging. That is actually a security risk. KSM allows the hypervisor to merge identical memory pages from different VMs into a single physical copy to save space. Attacker can exploit this to detect what is in the another VM's memory. For security sensitive environment, KSM must be disabled. So these are the memory boundary. Next is the AMD Save and Intel TML memory encryption. This is the most advanced memory isolation technique available today. AMD secure encrypted virtualization and the Intel's total memory encryption actually encrypt the memory in plain text. Even if someone has the physical access to the server, puts a probe on the memory bus, they only see the encrypted data, not the actual information. This represents the fundamental shift from trusting the hypervisor to not needing to trust it. Even if the hypervisor is compromised, your VM's memory remains secure. So these are the famous memory isolation techniques which are used from from the 2000s to till today. Next, we are going to see the CPU and the cache isolation. Let's talk about the CPU and the cache isolation because the CPU itself became a channel for the data leakage. So let's see this. Let me put the slide. This is the CPU and cache isolation. In this thing, first is the vCPU scheduling and the CPU pinning. These are known as each VM gets virtual CPUs. The hypervisor scheduler map this physical CPU cores. By default, multiple VMs might share the same physical core, switching between them rapidly. This creates the opportunity for side channel attacks because of shared CPU state. CPU pinning solves this by binding a VM's vCPU to a specific dedicated physical core. The core is never used by any other VM. This eliminates many context switch side channels. Then the next is the Intel cache allocation technology, which is CAT, which is also known as CAT. This is one of the most important isolation techniques. The L3 cache, the large shared cache on a CPU, is shared between all the cores. This means different VMs run on different cores are using same L3 cache. Attackers attackers can exploit this by measuring the cache time, how fast or how slow accessors are. To infer what another VM is doing, this is the basis of flush plus reload and prime plus probe attacks. Intel Cat solves this by dividing the L3 cache into separate portions called the cacheways and assigning specific ways exclusively to each VM. VM1 uses cacheways 0 to 7 and the VM2 uses cacheways 8 to 15. They never serve as cacheways. This eliminates the cache timing slide channels. So these are the Intel Cat. Next is the CPU feature and spectral mitigations. The hypervisor can mask or disable certain CPU features from being visible to the VM, restricting dangerous capabilities. For spectral vulnerabilities, specifically, there are several mitigations. Redpo line replaces indirect branch instructions with safer alternatives. Uh, IBRS, IBP, and STIBP are the microcode level control that restrict speculative execution across the security boundaries. Regular microcode updates from Intel and AMD are essential to current. Keep these protections current. So these are the CPU feature masking and the spectral mitigation. So next topic is the network isolation technique. Because VMs on the same host communicate through shared virtual network that creates one set of risk. So if we see the network isolation technique, if we see the block diagram, there is VM1 1098, VM2 1090, VM3 1098. Then there is VLAN 10, VLAN 20. They are all connected to the virtual switch. So if we look deeper into the VLAN segmentation, first is the virtual LANs. The virtual LANs use something called uh, 802.1 tags to logically separate network traffic. Even if multiple VMs are connected to the same virtual switch, a VM in VLAN 10 cannot see traffic from VLAN 20. They are completely separate in a separate broadcast domains. Co-resident VMs from different tenants cannot intercept each other network packets through VLAN segmentation. So segregation or segmentation. And next is the software-defined networking, also known as virtual firewall (SDN). SDN goes further. It uses programmable software to define exactly what traffic is allowed between any two VMs. Unauthorized traffic gets dropped at the virtual switch level. This prevents lateral movement, where an attacker who has compromised one VM tries to attack other VMs on the same network. The next is the SRIOV, single root IO virtualization, in which this technology allows a physical network card to present itself as a multiple independent virtual network interfaces called the virtual functions. Each VM gets its own dedicated virtual function. It bypasses the virtual switch entirely. This eliminates the virtual switch as an attack surface. Next is the encrypted overlay networks. Even with all of the above, network traffic between VMs can be potentially be intercepted. Technologies like VXLAN, uh, GE, Genevieve, tunnels with IPsec or WireGuard encryption ensure that even if traffic is somehow captured, the payload is completely unreadable. Tools like Calico, Cilium provide microsegmentation, which is ultra-fine grained network policies down to the individual container or VM level. So these are the network isolation techniques famously used today. So next we are going to see the storage isolation. Storage is another area where isolations can easily break down. Let me walk through the VM storage. VM storage is isolated. This is the VM storage isolation. If we look at the first is the virtual disk isolation, in which each VM gets its own virtual disk image stored in formats like VMDK, QCOW2. These are the files on the host system. Each VM only sees it in one disk image. The hypervisor ensures no VM directly access another VM disk file. However, snapshots and the cloned disk need careful access control. A snapshot might contain sensitive data from the original VM. Then the VM disk encryption. Full disk encryption using DMCrypt BitLocker inside VM. So full encryption has been done by the DMCrypt. Hyperload encryption has been done per VM AES 128 by 256 keys. Encrypted disk leak no data, even with physical media. Next is the input-output memory management unit and the DMA processor. Where when a VM has a physical device passed through it, like a GPU or a storage controller, the device can perform direct memory access, which means it can read, write physical memory directly by bypassing the CPU. Our input-output memory management unit actually prevents this. Okay. Next is the IO scheduler isolation. This is subtle but it is very important because when multiple VMs share the same storage backend, they share IO queues. The timing of IO operation can create a covert channel. One VM can interfere what another VM is doing by watching how long its own IO operations take. Dedicated per VM IO queues and the IO throttlings using IOPS limits prevent this kind of based information leakage. So the next is the side channel attacks on VM. These are the side channel attacks on VM. The side channel exploit observable physical effects of computation, not software bugs. Uh, these are the first one is the flush plus reload and the prime flush probe CPU cache attack. The L3 cache is shared between all CPU cores. An attacker is the one VM flushes a set of cache lines and clears them. The next is the Spectre branch predictor attack. Modern CPUs try to be very clever. When they reach a branch in code, like an if a statement, they guess which way it will go and start executing speculatively before they know for sure. If they guessed wrong, then they throw away the speculative. Spectre exploits this. Attacker mistrain the branch predictor. Meltdown. Meltdown is the out of order execution attack. Then there is a row hammer, which is the DRAM attack. This one attacks the physical hardware itself, not software at all. So this is the raw hammer. Now let's get into the advanced isolation. Advanced isolation, which is the TEE, micro VMs, and those containers, all those containers. First is the trusted execution environment. We have been talking about trusting the hypervisor to enforce isolation. But what if the hypervisor itself was compromised? What if a rogue cloud provider, employee, or sophisticated attacker gains control of the hypervisor? If your VM data is still stored. Trusted execution environment. Answer this question. The idea is to create a isolated memory region, isolated memory region that even hypervisor cannot read. Then there is the Intel Intel SGSAT, AMD SEV SMP, ARM Trustzone, Micro VMs, Firecracker and gvisor, container isolation hardening. So these are the advanced isolation techniques. Now we are going to compare all the all the types of this isolation in our next slide. So these are the comparison table. So if we see that in real deployment, we have to make choice based on your specific needs. All these techniques compare against each other. Look at this. EPT is excellent for memory protection, but it doesn't help with the CPU cache isolation or side channel defense. Intel CAT is excellent specifically for the CPU and the cache isolation. It directly caches them, but doesn't help in the memory or network security. Same with the IOMMU and the VTD. Excellent for IO security, uh, essential when passing through the physical devices to VM. VLN and SDN are excellent for network security, but they don't help in the memory or CPU isolation. AMD SCV is excellent for memory protection. It provides, strongest memory confidentiality. Micro VMs like Firecracker provide good protection across all dimensions by dramatically reducing the attacking surface. Gvisor provides good scale level isolation, but has higher performance over it for systems called heavy workloads. The most important lesson from this comparison is no single technique is sufficient. You need multiple layers working together. That's the principle of defense in depth. Each layer covers the weakness of others. So the next slide is the security and the best practices case study. So these are the security best practice and case studies. So there's a real world incidents. You can see the uh, 2018 Spectre and 2015 Venom, 2019 Indies attack, and 2021 L1 terminal. So these are the defense in depth. We need to use apply the CPU and the hypervisor patch immediately when new vulnerabilities are discovered. Speed always matters. Enable IOMM input output memory management unit in every host. Disable KSM. Implement strict VLAN segmentation. Use AMD SV or Intel TDX for any workload involving sensitive data. Deploy Firecracker or Kata containers. Contact regular penetration testing. Looking at the real world incidents, which showing that even most advanced isolation technologies are not, invincible. So these are the security best practices and the case studies. So if we go now, we jump into the conclusion of this session. So what we can take away is the first: no single isolation technique is enough in the world. You need layers, more layers. Uh, any isolation technique can be broken one day easily. So we need to advance them daily. Second, hardware level attacks are the hardest to defend against. Third is the AMD, SV, and Intel TDX represent the future of our cloud security. Fourth is the micro VMs like Firecracker offer the best balance. And the fifth is the performance over it, which is real but acceptable. Sixth is the threat landscape. Never stop evolving. I want to leave with this the final thought that VM isolation is not binary. It's not secure uh, or not secure. It is a spectrum of overlapping controls. Strongest guarantees require both hardware features and software hardware hardening working together. The cloud runs the modern world, and the security of cloud depends on how well we implement and maintain our VM isolation. So, thank you so much.